Welcome to our discussion on simplifying variable expressions. If you watched the other video on just evaluating them, it was a basic, simple introduction to it with one objective. Now we've got a bunch of objectives, but really it all boils down to one objective of simplifying them. We're just going to see how we can simplify them using different types of things: addition, multiplication, distribution, moving stuff around, and then we'll try and sum it up at the end. So let's start with the easy one. Let's simplify an expression using addition. Well, we can only add like terms, and like terms are things that have the exact same distribution of variables. So when you have a constant term, they have the same distribution of variables because they have none, right? They have no variables of any powers whatsoever. These two are like terms because they also have the same distribution of variables. They have an x, and they only have one x, right? An x to 1 power. This one is not because it's x squared. It's another power of x. So you have to make sure, and if there was another term, let's say that it was, plus 3xy. If we had something like that, where plus 3xy. Well, sure, that has one x, like these, but it also has a y. So it has a different distribution of variables, right? It's got a power of y. So that's no good. It's not a like term. Here's the distribution property. You've seen this before with numbers. Now we're just doing it with letters, right? If you have anything, right? Anything, it can be a number, it can be a letter, it can be any basically object that can be multiplied, and you're multiplying it by some stuff stuck inside some parentheses, then every term, right, and terms are things that are separated by pluses and minuses, every term gets multiplied by that piece. So in its most generic basic sense, when you just have these three letters, you get AB plus AC. But it can get more and more complicated. The idea is still the same. 2 times each of these means you're going to do 2 times 3 plus 2 times 4. But, that's kind of silly. We know that 3 plus 4 is 7, so we would just do 2 times 7. We would get 14, right? So we're just proving to ourselves that this property works with numbers, so we know that it'll work with letters. Here's another example. You can look through that really quick. All right, so what about that? We saw that second example where we had the number on the right-hand side of the pair of the parentheses, and it also seemed to work. Well, yes, it does. The distribution property works if the thing is being multiplied on the left side of the parentheses or the right side of the parentheses, because that's really coming down to, if you remember what it's called, the commutative property of multiplication, where we know that a times b equals b times a, right? A times b is the same thing as b times a. It doesn't matter in what order we multiply two things, it's still the same. Well, in this case, right, the parentheses is taking the place of b, right? Here's b and a, right? And here's, when you do it in the other direction, if you had a times b plus c, that's the idea of a times b, right? So it doesn't matter in which direction it is. Two things being multiplied together, this is one object, and then A is our second object. Those two objects being multiplied together, doesn't matter in which direction, it's still going to be the same. And I apologize, I shouldn't have used B because it's not the same B that's up there. That could be kind of confusing. I should have done X and Y, but you get the idea. X times Y is the same thing as Y times X. Well, if the distribution property works, then the reverse also works, right? If we have 2x plus 3x, then we can factor that x out and have 2 plus 3 times x. And it doesn't matter if the x is here or on the front side. It still is good. And then we know that 2 plus 3 is 5, and that gives us 5x. So it's kind of a way to prove to ourselves that we can add like terms, because these are two like terms, right? They're both the same distribution of variables. They both have just a single x. So we can do the same thing here, right? 5y minus 11y, well, isn't that just 5 minus 11 times y, or negative 6y? So we're using the distributive property kind of in reverse to remind ourselves that we can clean up expressions, and thus equations. Once we take it a step further, we can clean them up by combining like terms. Okay, the associative property, if you remember that, just tells us that if you have three things that are all being added together, you can take them in clumps. You can do A plus B first and then add C, or you can do B plus C first and then add A. And in fact, if you expand this out to however many numbers you want, you can basically take them in any order. As long as it's all the same thing, right? As long as it's all addition, then you're good to go. So here's a simple example with numbers, right? Where first we get 12 plus 15, or we can do 5 plus 22, but they both give us 27. So we're just proving to ourselves that that property works. The commutative property, I talked about it for multiplication. Here it is for addition, right? So we can add in either directions. A plus B is the same thing as B plus A. But what about subtraction? Is A minus B the same thing as B minus A? Hopefully you're all going, no, it's not. It's very simple to see that that's not the case. I mean, look at a very simple, easy example of 10 minus 3. Is that the same thing as 3 minus 10, right? Move them around and you go, no, this is 7 and this is negative 7. They're not the same, right? So it doesn't work with subtraction, and it also doesn't work with division, right? So the commutative property only works for addition and multiplication. It does not work for subtraction or division. I think I might have said that wrong, but it does not work for subtraction or division. All right, how about the additive property of 0? We know that anything plus 0 is itself. So that is called the additive identity. The inverse property just says that for any thing that we have, right, any number, there's going to be another number that is the additive inverse, so that when we add those two things together, we get that identity. The additive identity is 0. So that's A, and then negative A gives us 0. These are all kind of no-duh things. They're really just reminding you of stuff that's going to help you to simplify stuff, because you know that if you have 8x and then you subtract 8x from it, right? So basically 8x plus a negative 8x, well, those are identical things, but one of them is negative. So when you add them together, they become 0, right? So you're still using that same identity property. All right, how about the same stuff for multiplication? When we did addition, we're going to see all the same rules for multiplication. We've got the associative rule for multiplication, right? ABC is the same thing as A times BC. We've got the commutative property for multiplication. We've already talked about that. AB is BA. We have the multiplication property of 1. You know, before we had the addition property of 0. Now we have the multiplication property of 1, because A plus 0 is A, but now A times 1 is A, because obviously A times 0 is 0. So the identity for multiplication is 1, just like the identity for addition was 0. And since we had inverses for addition, we're going to have inverses for multiplication, right? If you have any number and then you take 1 over that number and multiply them together, you will always get 1, right? A times 1 over A is equal to 1. So these things are basically multiplicative inverses of each other, but since multiplicative is such a difficult word to say, we're like, oh, well, let's give it an easier name. We'll just call it the reciprocal, right? So 1 over A is called the reciprocal of A because it's easier than saying multiplicative inverse. Okay, next, simple example, duh. How about this? We want to simplify 2 times negative x. We know that the negatives basically go together. It's just negative 2x, right? What if the negative 2 was on the outside and the x was on the inside? Still be the same thing. What if it was a negative 2 on the outside and a negative x on the inside? Wouldn't it then be positive x? Yes, because we know negative times negative, right? So here's an example of the negative on the outside. We bring the negative on the inside. And hey, how come we're not doing negative 2 times x squared? Well, that's because the 3 and the x squared aren't individual terms, right? When we distribute, we take this number and we hit every term. There's only one term in here. These things are all clumped together because there's no addition or subtraction in between them. All right, so that brings us to the distribution property that we've already talked about. A times B plus C, right? It's times each piece. So when we do 3 times this, we get 3 times each piece because they're separated by pluses and minuses. All right, so here's another example of it. So let's see how we can simplify some expressions using these rules. So if I want to simplify all of this junk, well, it's usually a good idea to get rid of grouping objects, and parentheses are a version of grouping objects, and we get rid of parentheses by actually doing the distribution. So you multiply everything by 4, right? You distribute it through and you get your 4x minus your 4y. Then you take the negative 2, right? Because this is really plus a negative 2. So you take that negative 2 all the way through. Negative 2 times negative 3, there's my 6x. Negative 2 times positive 6, there's my negative 12y. Now I can take this many x's and this many, right? There's 4, 6, there's 10 total. And then we've got negative 4, negative 12. There's my negative 16, right? So there's how all of this comes together to simplify these expressions, which is what we're going to use when we have to simplify equations. Here's one last example. You can work through that, and then let's move on to some more complicated stuff.